Hi everyone. So looking at this paper, I think you know what this video is going to be about maths. Specifically, it's going to be about the maths of the coronavirus. We're living in very interesting times, and I thought maybe, just maybe, I could make a mini video about, or maybe not so mini, but it's going to be quite hairy, but a video about the logistic equation, also known as the Verhulst equation, which is essentially is very different to any other model of population growth, because normally when we talk about, for example, bacterial growth, there's this kind of very sensical idea that as the population begins growing, the rate may not be so high, but then as there's more bacteria because they reproduce, more bacteria is grown, and so we kind of end up with this exponential rising pattern. But actually this is far from reality for most populations. So as you can see in many news websites, in many countries, the reported cases of coronavirus are decreasing. The reason for that being that there aren't enough people for the virus to catch, because say if one person is infected, they're going to stay at home and look after themselves, so then that person is not going to go outside anymore and he won't be exposed to the virus and so forth. Or if that person has already got the virus, he would have gotten immunity, or at least for the next month. So this is a very interesting pattern, and it can be beautifully described using the language of mathematics, which I'm going to share with you right now. So what I mean by what I just said now is we can have a certain population, like a starting population, like an initial value for n, and it can be anything. Again, it could also be humans growing. It can be animals. It can be anything. And so we start with this initial value, and as there's more of it, the rate of change, the rate of growth increases. A bit like an exponential model, but then as there's a constraint in the amount of space available, or food, or whatever that is, it starts decreasing again, leaving us with this kind of plateauing shape, like an S shape. And it doesn't have to be symmetrical. I just didn't plan this correctly, but it's generally a sigmoid kind of S shape. And so this can be described as follows. So we can say that the rate of change in growth, dn over dt, because we measure it against time, we can say that is equal to r, which is the rate, times n, times 1 minus n over k. And what is k? K is this line over here, so k is essentially the capacity of this population. So say if we have, it's kind of relating to my experiment. If we have like a jar full of sugar and whatever, proteins and bacteria growing in it, obviously they're going to go exponentially as there's more food and for the new bacteria to actually grow in it and reproduce themselves. But then at some point we're going to hit a point where there's not enough food, and we're just going to start decreasing the amount of reproduction until we just all die, pretty much. This could be applied to any other scenario, but this is just a basic example. And so this equation makes sense, because if you think about it, n over k is a ratio between the current population and the capacity it can handle. So if the current population is like only 2 and the capacity is 1,000, then of course 1 minus that is going to be quite close to 1, and then times n times r, it's going to be quite a high rate of change. But then if we look at when n is close to k, then 1 minus n over k is going to be pretty much 0, hence the flattening of this curve over here. And so I'm going to start and actually do this. So one really useful technique for it is just first order differential equations, separation of variables. So I'm actually going to go on and take this bit over here, divide it. from both sides. So we have 1 over n times 1 minus n over k dn d over dt. That's going to be equal to r. So you see, very asymmetrical looking over here. So what we're going to do now is we're going to move dt to this side. Not that it really matters at this point, but I just think it's neater. And my teacher pointed out that this on its own wouldn't really make sense because algebraically dt doesn't mean much. So we're going to actually go on and integrate. It doesn't matter, it's just an extra step, and actually doesn't, as I said, it doesn't really matter, but it looks more mathematically correct. Okay, so then we're going to use partial fractions to solve this, which is going to be actually quite long, but easier than you might expect. So we do the usual substitution, so a over n plus b over 1 minus n over k, and that's going to be equal to 1 over n times 1 minus nk. Hopefully this makes sense so far. And then, yeah, if we times both sides by n times 1 minus n over k, we're going to end up with a times 1 minus n over k plus bn equals 1. So that's neat. We can generate quite a lot of simultaneous equations using that. And so that's what I'm going to do. I'm just going to go on and substitute n equals 0 because it's easier. In this scenario, we would have 1 times 1 minus a times 1 minus 0 plus 0 equals 1. So then a times 1 plus 0 equals 1. That clearly implies that a equals 1 itself. So that's quite neat. Now we need to work out b. So if n equals k, on the other hand, then we end up with a ratio k over k, so that's minus 1, then 1 minus 1 equals 0. So a times 0 plus bn equals 1, and we said n equals k, so bk equals 1, hence b equals 1 over k. And here we can progress on to some natural logarithms. So we need to rewrite the system, this equation, sorry. And so we can just say everything we've done here essentially. So splitting it to partial fractions, because that's much easier to integrate. Then, I don't know why I'm doing I, just to show that it didn't come out of nowhere. Anyway, so I equals the integral of 1 over n plus 1 over k, because remember b is 1 over k, divided by 1 minus n over k. Simple. And that's the integral of r with respect to t on the other side, which is, as you're going to see, just going to be rt, so nothing, no biggie. The big part of this solution finding is just the left hand side. So 1 over n, we know, respect to n, integrate that. That's going to be ln of the absolute value of n, and I'm going to change it soon to make it more neat, but for now let's focus on this. Okay, so then we go on and we see that actually this is very similar to this expression over here, it's just times by n. And the derivative of the denominator here would be, ignoring the constant because they differentiate to 0, that would just be minus 1 over k. So using guess and check, as my teacher calls it, we can just kind of see that this numerator here is just the derivative of the denominator times minus 1. So minus ln of 1 minus n over k, okay? And we have a constant, but let's just save as a constant. Equals rt plus a constant as well. We can give them numbers, it doesn't really matter at this point. And so we say that ln of n minus ln of 1 minus n over k equals rt plus one big constant, which is, in fact, it doesn't really matter. It's c2 minus c1, but it's just a constant. But it seems like I'm kind of running out of time, so I'm gonna continue this video in 3 minutes, and I'm gonna do all the cool bit. This is just kind of a preparation of a less hairy expression we can work with more easily. I'm gonna do the rest in the next video, so see you soon.